So today we're going to be looking at a rotometer, and we're going to be using the height of the ball to determine the volumetric flow rate of the liquid inside the ball. So this gap is actually supposed to be extremely small, but I'm going to draw it slightly bigger just so we can see it. So there's 3 points that we're mainly interested in, but we'll start off by saying the diameter of the sphere is going to be d0, and we have point 1, and we're assuming that the liquid is flowing either up or down. The liquid's not stationary, but the ball is. So anyways, we have point 1, and there's going to be a pressure at point 1, point 2, and there's going to be a pressure at point 2, and point 3, and there's going to be a pressure at point 3. We can say that P2 is roughly equal to P3, because between point 2 and point 1, we're assuming that this cross-sectional area A2 is extremely small relative to the cross-sectional area of point 1 or point 3. So we have a volumetric expansion, or a sudden expansion, excuse me. So we can say that P2 is equal to P3. And we know that the relative weight of the ball, or the force exerted because of the relative weight of the ball, is going to be equal to the difference in density between the fluid and the ball times gravity, and then times the volume of fluid displaced by the ball, or the volume of the sphere. And we're going to assume that this is a perfect sphere. And we're also generally assuming that the density of the ball is greater than the density of the liquid it's in, usually water. But anyways, so we're going to say that the volume of the sphere is pi d0 cubed over 6, I believe. And then that's going to be equal to 0 because the ball isn't moving. It's at a constant height, no acceleration up or down. Well, since there's no acceleration up or down, but we know that we have a pressure force exerted by P1 and P3, we're going to assume that, well, we're not assuming, we know that P1 minus P3, the force is exerted by the pressure differential, is going to be equal to 0. So we can substitute that in. We're going to have P1 minus P3, and like we said, P3 is equal to P2 times the cross-sectional area to get the force. So pi d squared over 4. And you'll notice that this is starting to look like something we see in Bernoulli's equation, specifically when we move the pressure term to the other side. So hint, hint, we're going to be doing that in a little bit. So we want to solve for this P1 minus P2. So we're going to have rho E minus rho F, difference in densities. And then if we multiply across, we'll have 2g d0 over 3 equals P1 minus P2. All right, I don't know why I have all these scraps here. All right, anyways. So going back to Bernoulli's equation, we have P2 minus P1 over the density of the fluid minus V2 of velocity at point 2 minus velocity at point 1 squared over 2. And typically we'd have a gravitational term here. But we're going to assume that the difference in height between point 1 and point 2 is going to be negligible. So we're going to say that's 0, and we're also going to ignore frictional heating for now. So in this case, we're going to solve for V2. We could solve for V1 if we really wanted to. But we're going to say that the total, the velocity times the area at point 1 is going to be equal to the velocity times the area at point, not 3, 2. So solving for V1, we have V1 is equal to V2 A2 over A1. Plugging that in and substituting, we have P2 minus P1 over the density of the fluid minus V2 squared over 2. And I'll go ahead and substitute that out. So 1 minus the V2 squared will be substituted out. So we'll be left with A2 over A1 is going to be equal to 0. Now, like we said before, we're assuming that A2 is extremely small relative to A1. So A2 divided by A1 is going to be very, very close to 0. So we can go ahead and replace that with 0. And we'll be left with P2, sorry, what am I thinking? Plus V2 squared over 2. It's going to be equal to P1 minus P2 over the density of the fluid. And then we can substitute in our expression here. So we're going to have, I'm trying to do this from memory, so I'll go back and check in a second. Fluid, and we have 2/3 diameter. So we'll have 2 times the diameter over, sorry, I'm checking if I'm recording. Got scared that my audio was off. Anyways, so we're going to have 2 times the diameter over 3. And then that'll be divided, whoops, over 3. And we can go ahead and just move the 3 down. So we'll have 3 times the density of the fluid. And then just multiplying across and taking the square root, we have the velocity at point 2 will be equal to the square root. I'll do the square root last, actually. We'll have the difference in oh my god, rho. Okay, there we go. Difference in densities times 2. And it looks like I dropped a g here, actually. Times 2 times the diameter times g over 3 times 2. So we'll have 4 here. And then the square root of that. So from here, we can remodel our rotometer so we can express this in terms of height, because as it stands right now, this would give us the volume or the velocity given the diameter and the density of the fluid in the bowl. But we're more interested in determining this due to the height. So now we're interested in relating this to the height of the sphere in a rotometer. So in a real rotometer, you'd have sloped sides, so there's a sort of taper. I'm going to exaggerate it for this. And then we'll have this larger diameter and this smaller diameter, D0. And we'd have the ball somewhere in here. And the slope of our thing, the slope of our rotometer is just going to be represented by what I usually is m. And we know that the new diameter of this is going to be equal to our original diameter plus mh, because if you have a slope m and then a height h, this increase here is just going to be m times h. From there, we're interested in finding the cross-sectional area right here that goes all the way around the ball. And we can express this as keeping this d0. So we're saying that this part of the taper is equal to this height, or the diameter of the ball. We're going to say that this diameter is still d0. This is d. And don't get confused by this. We're just saying that large d is just going to be d. It's based on the height of the ball given this expression. But anyways, we're interested in finding the total height of, or the total surface area, or cross-sectional area is a more accurate term, of this portion. So we know that the cross-sectional area is the diameter squared over 4 times pi. So the actual cross-sectional area of this is going to be the larger cross-sectional area, this whole area, minus the smaller cross-sectional area, the cross-sectional area of the ball. So we're just going to have d squared times pi over 4 minus d naught squared times pi over 4. And that's going to be equal to our cross-sectional area at point 2. So now looking back at our expression up here, we solve for V2. Well, we know that a volumetric flow rate is still Q equals V2 A2, and we just solve for A2. So replacing this, and we're going to also substitute in this D naught plus MH in for our D squared. We're going to get V2 D squared times pi over 4 minus D naught squared times pi over 4 equals Q. So we can go ahead and substitute out a pi over 4. So we'll just be left with D squared minus D naught squared. And then we can substitute in this D naught plus MH for D squared. So we'll have D naught squared plus 2 D naught M H. And then plus M squared H squared minus D naught squared equals Q. And then these two D naughts will cancel. And then, like I mentioned before, usually the slope of this is extremely small. Now, it's not necessarily something we need to ignore, but in this case, we're going to assume that it's extremely small. And when you square an extremely small number, you get an extremely small number. So this is essentially 0. And so we're left with V2 times pi over 4. And then we'll just be left with 2D naught M H. If we really wanted to, we could leave that expression in there. It wouldn't change things that much. But for now, we're just going to take that out. And then that's going to be equal to Q. And then, as before, we can substitute in this expression here. I don't know how to copy with this pen. I'm going to see if I can do this from memory. So we're going to have the square root. That's still lasso. So we're going to have the square root of, I believe, the density of the ball minus the density of the fluid times 4 dog D naught times G over 3. Yep. Quite proud I got that. I think I'm using red. Don't blame me, I'm colorblind. Anyways. And that is going times pi over 4. And you know what? I'll put the pi over 4 on this side. And then I'll put the 2 D naught M H on this side. And that is going to be equal to our volumetric flow rate. And just prettying it up a bit, we'll have 2 pi over 4, and that's just going to be 1/2 pi. So let me go ahead and do that. Pi over 2 square root of our volumetric, difference in densities times 4 times D naught times G over 3, and then times D naught, our slope times our height, will be equal to our volumetric flow rate.